The broadcast is now starting. All attendees are in listen-only mode.
Hello, everyone, and thank you for joining us today. You've logged on to the Nelson Labs webinar, Antimicrobial Surfaces, Finishes, and Treatments, Understanding Testing Options. Now, if you miss one of our webinars or would simply like to refer to one, you can always find them on the Nelson Labs website on the On-Demand Webinars page listed under Education. You can receive notifications of upcoming live and on-demand webinars by liking Nelson Labs on Facebook or following on Twitter and LinkedIn. We also invite you to register for free for the Sotera Health Academy at soterahealth.com/academy. There, you will find curated content from industry thought leaders, from introductory sterilization and lab testing topics to advanced in-depth learnings. Our expert advisors have filled this academy with cutting-edge educational content and resources to help you mitigate risk, go to market faster, and achieve excellence in your field. Nelson Labs is a leading global provider of laboratory testing and expert advisory services for healthcare, consumer, medtech, and pharmaceutical companies. The company performs over 800 rigorous microbiological and analytical laboratory tests across the medical device, pharmaceutical, and consumer industries. The experts at Nelson know every test matters and requires solutions to complex problems to improve patient outcomes and minimize client risk. And now, let's get started. Today, we're joined by Terry Eastman and Kelly Birmingham. Terry is a highly accomplished microbiologist who received her degree from Montana State University. She has extensive expertise in microbiology study design, regulatory compliance, and product claim substantiation. Ms. Eastman has worked at our Bozeman, Montana lab for over 25 years. Her exceptional skills and expertise have enabled her to become a key resource to sponsors looking to perform antimicrobial evaluations. Kelly is a highly qualified virologist and has been a key member of the Nelson Labs Bozeman team for over 15 years. Currently, Kelly serves as a study director 3 at the virology laboratory at our Bozeman facility, where she plays an instrumental role in offering expert guidance to our sponsors on virus testing requirements. We do encourage your questions, so please submit them at any time in the questions box. Kelly and Terry will try to answer as many as they can in the last 10 to 15 minutes of the webinar. Now, beginning today's presentation, I turn the time over to our presenters.
Good morning, and thank you for the introduction, Daniel. Today, Kelly and I will be talking about antimicrobial surfaces, and we'll be discussing the various testing methodologies commonly used for evaluation of antimicrobial efficacy. To start with, we'll be providing a general overview of what antimicrobial surfaces or finishes are and the most commonly seen applications. An antimicrobial surface is a surface that either contains or is coated by an agent that inhibits the ability of microorganisms to grow on the surface of the material. This can be the result of the surface repelling a pathogen and preventing its attachment to the surface in the first place, often referred to as an anti-fouling coating, or the result of the surface actually killing or inactivating pathogens that attach or are too close. This is commonly referred to as an antimicrobial coating or surface. There are different mechanisms of antimicrobial activity, depending upon the type of surface and its intended area of use. Antimicrobial activity can be related to the chemical composition of the surface. Generally, this can include the addition or bonding of an antimicrobial to the surface substrate. These can be antibiotics, compounds such as organosilines, and quaternary ammonium compounds, or also antimicrobial peptides. Antimicrobial activity can also be related to a physical modification of the surface structure itself, such as a change in the roughness of the surface, as with micropatterned surfaces, or creation of a superhydrophobic surface. Finally, antimicrobial activity can be related to the presence of metallic ions within a solid surface, such as with copper and copper alloys, as well as silver. Depending on the application, the activity of an antimicrobial surface can be specifically targeted as either bactericidal, virucidal, fungicidal, or a combination of these. Even before the onset of the pandemic, antimicrobial surfaces were becoming more and more widely used in healthcare as well as in routine day-to-day or consumer settings. Some of the more common antimicrobial surfaces found today include touch surfaces, medical devices, fabrics, textiles, and linens, and even building materials such as ductwork and plumbing. In hospitals and healthcare environments, antimicrobial touch surfaces are intended to prevent patient-to-patient, healthcare worker-to-patient, or visitor-to-patient transmission of germs. Such surfaces include door handles, faucets, and bedside railings. In food prep and food processing environments, these antimicrobial surfaces are intended to prevent cross-contamination with germs causing foodborne illnesses. Examples include food contact surfaces such as cutting boards, shelving in food storage containers, utensil handles, and storage bins. In the household, antimicrobial door handles, light switches, kitchen surfaces and countertops, and flooring are becoming more common, as are faucets, shower walls, shower curtains, and backsplashes in bathrooms. Antimicrobial surfaces are now routinely used in commercial and manufacturing environments and have become a hot topic for personal as well as shared items such as cell phones, office furniture, and keyboards. Antimicrobial paints are becoming much more common as well, with targeted use in healthcare facilities, schools, offices, and gyms. Medical devices with incorporated antimicrobials are becoming much more prevalent, with the goal to better control hospital-acquired infections. Examples would be extended use medical devices such as catheters and lower access devices, medical electronics and bedside monitors, medical implants such as orthopedic implants and joints, and surgical masks and face coverings, as well as wound dressings and bandages. Antimicrobial fabrics, textiles, and linens are also now common, with a focus on medical drapes and linens, air filters, and consumer use fabrics and clothing, such as socks, athletic clothing, and equipment. And finally, antimicrobial building materials such as ductwork and plumbing are becoming more prevalent in order to address mold prevention and indoor air quality, as well as drinking water safety. We're going to start by discussing two qualitative methods for evaluation of antimicrobial efficacy, which most of you may already be familiar with. The first is a zone of inhibition evaluation. This is also known as a Kirby-Bauer test. In a typical zone of inhibition test, a petri dish containing a nutrient agar is swabbed or streaked with a bacterial culture. A sample of a product treated with an antimicrobial agent is cut into a piece, typically 1 inch by 1 inch, and placed onto the agar surface. The petri dish is incubated overnight, allowing a dense lawn of the bacteria to form. For test materials where the antimicrobial agent can migrate into the agar media around the sample, an area of clearing or a zone where the bacterial growth is inhibited may be visible. This is illustrated in the upper figure. This method is simple and quick and allows for high throughput examination of many samples side by side and can be used with a wide variety of bacteria, yeast, and fungi. This method can also be modified to allow for measurement of the durability of an antimicrobial coating over time. For example, samples can be transferred daily from one agar plate to fresh agar plates to see how long the antimicrobial activity is maintained or how many days a zone of clearing is observed. The method does have some limitations, however. The method does work best with flat pieces of product, and either plastics or textiles can be evaluated. The method does not distinguish between inhibitory activity, where the bacteria may still be viable within the zone of clearing, but cannot multiply and grow, and microbicidal or killing activity. Additionally, a lack of a visual zone does not necessarily mean that the antimicrobial agent is ineffective. The zone of inhibition test requires the antimicrobial agent to migrate into the nutrient agar. If the antimicrobial is not compatible with the nutrient agar, it will not migrate to create a visual zone of inhibition. While it might do a very effective job in protecting the product itself, The lack of a visual zone might falsely suggest that the antimicrobial is ineffective. Similarly, while a very large diffuse zone around a sample might indicate more antibacterial strength, it may also signify that the antimicrobial is not as tightly bound to the sample and may have a tendency to migrate out of it too rapidly. Lastly, there are no set standard pass-fail criterion for a sample. A second qualitative method commonly used is AATCC 147, also known as the parallel streak method. This method is very similar to the zone of inhibition test, but it is specifically written for treated textile products. It is commonly used as a screening tool, often to detect residual antimicrobial activity after exposing a fabric to repeated wash cycles. The main difference between this method and the zone of inhibition test is the inoculation of the agar surface. The organism is applied by streaking a single inoculum loopful across the agar surface 5 times in parallel streaks, hence the name. This is intended to result in a gradually decreasing amount of growth of the organism from one side of each streak to the other, or from the left side to the right side, as well as from the first streak to the last streak, thus providing a rough gradient of growth. A rectangular piece of the test material is placed across all 5 streaks and the plate is incubated. This is illustrated in the lower figure. The zone of clearing produced around the material is observed for each of the 5 separate streaks, which provides varying degrees of sensitivity across one sample of the test material. Again, the limitations of this test are similar to those already discussed for the zone of inhibition evaluation. While these qualitative methods can be a useful screening tool, a more in-depth measurement of the antimicrobial activity of a treated surface is often desired. And this is where the quantitative methods are useful. There are numerous methods routinely used. First, we will discuss AATCC 100, or the test method for antibacterial finishes on textile materials. This method allows for the comparison of the degree of antibacterial activity after a standard 24-hour exposure to a test bacteria on a treated fabric material, as compared directly to an untreated control. And this control is the same fabric, but with no antimicrobial added. For this method, a standardized broth suspension of a bacteria, typically Staph aureus or Klebsiella pneumoniae, is prepared and inoculated directly onto pre-cut pieces or swatches of the fabric. A standardized amount of inoculum, typically 1 milliliter, is then inoculated onto a standard 1 gram quantity of fabric. Samples are evaluated immediately by neutralizing in a rinse fluid, then diluting and plating. Additional samples are evaluated after exposure at 37 degrees Celsius for 24 hours, although shorter contact times can be evaluated. Plate counts for each sample are performed at each contact time, and the percent reductions as compared to the untreated control are calculated. It should be noted that this method is only applicable to textile or fabric materials which can absorb and hold onto the aqueous inoculum suspension. This method is useful in that it can also be used to monitor how well antimicrobial activity is maintained in a fabric after repeated washings or use.
So the next method is ISO 18184. It's antiviral activity on textiles. It's very similar to the one Terry just spoke about. It's specific for viruses. So fabrics are cut into pieces of 20 millimeter by 20 millimeter, and then up to a weight of 0.4 plus or minus 0.05 grams. Then the standard exposure that's listed in the method is 2 hours at 25 degrees. However, other contact times can be tested, but they should not exceed 24 hours. The virus suspensions that are described in this method are influenza A and feline calicivirus. However, they recommend that other viruses can and should be tested because they can't replace the data from these two viruses can't replace from another type of virus like coronavirus or any other virus. So testing is usually performed in 3 replicates. 0.2 mils of the virus is aliquoted over the pieces of textile over several points and then allowed to expose. The time 0 is only against the untreated control product, and then the control and then the test product will be exposed for the desired exposure time at 25 degrees. So the time to elute the virus, we add the neutralizing agent and then pulse vortex for 5 seconds, 5 times to wash the virus off of the specimen. And then we'll dilute and plate to determine the log reduction. So this method does have acceptance criteria. So good antiviral effect is described as less than 3 logs, but greater than or equal to a 2 log reduction. An excellent effect is a log reduction of greater than or equal to 3 logs.
The next quantitative method we will discuss is ASTM E2180, or the standard test method for determining the activity of incorporated antimicrobial agents and polymeric or hydrophobic materials. As stated in the name, this method is designed to evaluate the antimicrobial effectiveness of hydrophobic or polymeric materials, such as plastics. These antimicrobials typically require contact with the microbial cells for maximum activity. Problems arise when an aqueous-based bacterial suspension is applied to these types of materials because the surface tension in the polymer can cause the inoculum suspension to dome. Bacteria within the droplets of inoculum may not contact the treated surface if the surface does not dry, or if it does dry, the cells may become layered. As a result, low antimicrobial activity may be observed. The standard method addresses this problem by using an agar slurry as a vehicle for the inoculum, which reduces the surface tension and allows for more even contact with the test surface. This method also requires evaluation of an untreated material in parallel. In brief, a molten suspension of the bacterium is created in a semi-gelatinous fluid with a low agar concentration, and it is typically held at 45 degrees Celsius. This is known as a slurry. A thin layer of this slurry is then applied to the test and control surfaces to result in a uniform thin layer, approximately 1 millimeter in depth, and the surfaces are generally tested in triplicate. Samples are evaluated immediately and following 24 hours. Exposure can be done at the desired temperature for the test material, and contact times can be extended for more resistant organisms such as fungi and yeast. After each time of exposure, samples are neutralized in a rinsing fluid, then diluted and plated. The percent reductions, as compared to the untreated controls, are calculated. This method can also be utilized to evaluate continued efficacy over time, where samples are exposed to repeated washings or use and evaluated side by side with unwashed or new surfaces. 2 additional very commonly used quantitative methods are ISO 22196 as well as JIS Z2801. Both methodologies are useful for plastics. These 2 methods are very similar with different governing bodies. These methods are also very similar to the ASTM standard just discussed. The main difference is how the inoculum is applied to the treated surface. Rather than using a thickened agar slurry to achieve good contact, a broth suspension of the inoculum is applied to the plastic surface, and the inoculum is then covered completely with a layer of thin plastic film to ensure good contact with the surface. This is illustrated in the attached diagram. Standard species are recommended by these methods, and typically these are Staphylococcus aureus and E. coli. Treated test samples as well as untreated controls are evaluated, and usually a minimum of 3 replicates are prepared for each time point. As with the ASTM method, samples are taken immediately and at 24 hours, and exposures are done at 35 degrees Celsius. Again, samples are neutralized in a rinse fluid, then diluted and plated to result in plate counts. Antibacterial activity is measured by comparison to the untreated controls. Also, as with ASTM E2180, flat samples of each material are a requirement for testing.
ISO 21702 is the measurement of antiviral activity on plastics and other non-porous surfaces. This method is very similar to the 2 methods that Terry just discussed. It's except it's specific for viruses. The virus suspension is applied to the plastic surface, and the inoculum is covered completely with a layer of thin plastic film to ensure good contact with the surface, which is very similar to the diagram above. Standard species that are recommended by the method is influenza A and feline crucivirus. However, the method can be modified to test other viruses. Treated test samples as well as untreated controls are evaluated, usually a minimum of 3 replicates at each time point. Samples should be provided in 50 millimeter by 50 millimeter pieces, and then they're covered with a 40 millimeter by 40 millimeter piece of film. Samples are taken immediately on the test and the control, and at the exposure time, which can be any time up to 24 hours, and exposures are done at 25 degrees C. Then the samples are neutralized in a rinse fluid, and then they're diluted and plated, and then the log reduction will be determined from that information. And this method doesn't have any specific acceptance criteria, so it's based on the regulatory body or whatever is requested by the sponsor. And one recommendation for this study is your untreated control. You want to make sure that it's definitely inert, because sometimes if your material is only untreated, it can still have an antiviral effect. So if your untreated product may have an antiviral effect, you may want to use glass or another inert material.
Occasionally, the intent of an antimicrobial surface is to prevent microbial attachment in the first place, rather than to just kill microbial cells with contact. For these types of surfaces, there are several methodologies available that can measure the ability of a surface to prevent formation of this microbial biofilm. Modifications of 2 ASTM methods can be used for this type of testing. ASTM E2562 and ASTM E2647. In each of these methodologies, samples of the test surface are exposed to a low concentration of a nutrient broth containing the challenge species over a period of time under dynamic conditions. That is, there is continuous movement of a fluid with nutrients over the surfaces. Because of their very complex nature, we will only be providing a brief overview of these methods. The CDC reactor, displayed in the upper figure, is a vessel with 8 rods hosting removable coupons for a total of 24 samples that may be evaluated. The coupons are tailor-made from the desired test material or materials and then examined simultaneously in a single assay. Individual coupons can be removed or exchanged during the experiment, allowing time course studies. The rotation of the baffled stir bar within each reactor leads the coupons to undergo a consistent high shear. Nutrients are continuously pumped into and out of the reactor at the same rate. These stress conditions promote biofilm formation on the test surfaces. The drip flow reactor, displayed in the lower figure, is typically made of 4 or 6 parallel chambers each one containing a single coupon manufactured from the desired test material or test materials. The broth medium enters the individual chambers at the top through a needle. The reactor is kept at an angle of 10 degrees so that the liquid flows along the length of the coupons. Bacterial cells are grown under low shear and continuous flow, mimicking the environmental conditions found in indwelling devices and the human body, such as in lung infections, tooth biofilms, or microbial colonized catheters. In each model, the exposed surfaces are removed from the reactor at a defined time, and the attached bacterial cells are removed by scraping, then diluted and plated. Quantitative recoveries are calculated for each surface. Results can be compared between differing materials, both with and without incorporated antimicrobials. It should be noted that these are not high throughput testing methodologies, and biofilm formation is very species specific. Not all target species can be evaluated using these methodologies. Each of these ASTM methodologies were designed with strains of Pseudomonas aeruginosa. An additional biofilm method is available that specifically evaluates prevention of Escherichia coli biofilm in antimicrobial urinary catheters. This method is ASTM E3321. In brief, both antimicrobial and non-antimicrobial catheters are exposed to an artificial urine medium and then contaminated with E. coli. During the entire test, the biofilm is exposed to a continuous flow of artificial urine through the catheter. At the end of each specified time period, bacteria can be quantified by collecting the effluent fluid through the catheter, as well as by scraping the lumen of a segment of the catheter. Samples are diluted and plated, and microbial recoveries can be compared between the antimicrobial and non-antimicrobial catheters. Sample collection times are typically at 24, 48, 72, and 96 hours, simulating actual in-use conditions.
Next, we will briefly discuss methods for evaluation of antimicrobial surfaces for which EPA registration is desired. These two methods are EPA SOP MB41-00 and EPA SOP MB40-00. As background, in October 2020, the EPA issued interim guidance and test methods for public comment as a pathway for companies to add claims for residual efficacy to their products labels. Products with residual efficacy claims fall into two major categories: disinfectants, which we will not discuss today, and two, supplemental residual antimicrobial products, for example, coatings, paints, and solid surfaces. These specific products do not meet the EPA's standards for disinfectants, but are intended to be used as a supplement to standard disinfection practices. These products are outlined in the two right-hand columns of the table on this slide. So two very detailed testing methodologies must be followed to achieve registration claims for these products. One, to support a claim for a supplemental residual antimicrobial, which is a fixed solid surface, the EPA's method for the evaluation of antimicrobial activity of hard, non-porous, copper-containing surface products, which is the MB-41-00, should be used. And then to support a claim for a supplemental residual antimicrobial surface coating or film, the EPA's test method for evaluating the efficacy of antimicrobial surface coatings, EPA SOP MB40, should be used. Both methods describe efficacy requirements for the registration of products that are intended to provide residual antimicrobial activity for a period of weeks or years and are designated to be supplements to standard disinfection practices. The methods include an efficacy assessment of the solid surface materials or coated coupons following repeated exposure to specified chemical solutions with standardized repetitive mechanical abrasions using an abrasion instrument. The chemical solutions are representative of various disinfectants that the surfaces will come into contact with during normal disinfection procedures. So for example, bleach, there's peracetic acid and hydrogen peroxide, or quaternary ammonia products. The baseline efficacy of the antimicrobial surfaces, as well as the durability assessment, or efficacy over time and after repeated wear, is measured against Staphylococcus aureus and Pseudomonas aeruginosa and viruses. They typically recommend to test the hardest to kill viruses that are on your already approved label. The test methods can be adapted for additional organisms, and a minimum 3 log reduction of the organism within 1 to 2 hours is required for bacteria and viruses.
And finally, while the testing methodologies just discussed can be used to evaluate antimicrobial surfaces while in the developmental stages, most notably because flat pieces are generally required, such surfaces are often not representative of a final marketed product. In instances where data are desired for a finished product, such evaluations should take into account how the finished product will be used in its target environment and should be designed to mimic such a setting. Such evaluations might include evaluation of the finished product after a period of simulated use or following a period of repeated challenges. In general, these antimicrobial efficacy evaluations should include comparison of the test product with a control product which is identical but without the antimicrobial agent. It is also recommended to include a predicate or comparator product which is already commercially available for comparison purposes. For all such studies, consultation with the appropriate regulatory agency during the study design process and prior to testing may be necessary, and specific efficacy requirements may apply. This concludes our presentation. Kelly and I would both like to thank Daniel for his assistance with this webinar and are now open to any questions that you may have.
Thank you.
Kelly, Terry, thank you so much for your insights. We've all learned some great information today, and you've given us a lot to think about. We did receive some questions as you spoke, which we would like you to address now. Now, if we don't get to your specific questions today, our experts will be happy to address them individually after we conclude today. And so for the first question that we received today, it is for antimicrobial fabrics with multiple layers, such as a medical mask, how does the efficacy evaluation differ compared to a single layer product?
The AATCC 100 methodologies simply require that the swatches of the mask or the fabric be stacked such that they will be inoculated from the top and simply contain an entire 1 milliliter quantity of the inoculum. So the inoculum should penetrate through all layers of the fabrics and be exposed in that fashion. Now these methods will not evaluate the barrier potential of a mask under such conditions, just whether or not the entirety of the fabric sample will provide a log reduction.
Fantastic. Thank you so much for that answer. The second question that was asked was, is the ISO 18184 method virus specific, or can it be used with any viral strain?
It can be used with any viral strain. So whatever strain that you want to be able to show is what should be tested. It's just the method itself has specifics for influenza and feline calicivirus. And they actually recommend to test other types of viruses for your efficacy.
Fantastic. Thank you so much. And the final question is, do you recommend any methods for an antimicrobial claim on a powder product?
That's a good question. Generally speaking, for an antimicrobial powder product, we would most likely recommend a different version, probably design a study where the powder could be solubilized in some fashion, similar to a suspension time kill, but there would be some product development phases that would need to be incorporated because it's not necessarily a flat surface per se. So that would require some specific studies, consultation, study design to verify that what we would be proposing would actually provide repeatable, reproducible results.
Fantastic. Thank you again for that answer. That is all the time we have for questions today. But if we did not get to your question, we will reach out to you individually, or feel free to reach out to us directly at experts@nelsonlabs.com. Thank you both again for that thorough and informative presentation. I'd like to thank you, Terry Eastman and Kelly Birmingham, for your insights. And I'd also like to thank you, the viewer, for attending this session. I hope you found it to be a valuable experience. Please visit us at nelsonlabs.com for more on-demand and live webinars like this, and we hope you have a wonderful day.